And now in this lecture we'll find out the radius of the small circle. In the drawing we have a right triangle, triangle ABC is a right triangle. In addition, we know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. This is angle ABC, that is the right angle. Inside the right triangle ABC we have this small circle and this big semicircle, and our mission is to find out the radius of this small circle. Okay, so first of all we'll define the relevant points to this question with letters. We'll define the center of this small circle, this point, as point P. We'll define the center of this big semicircle, this point, as point Q. We'll define the point of tendency of tangent AC with this big semicircle, this point as point H. We'll define the point of tendency of tangent AB with this small circle, this point as point N. And we'll define the touching point of this small circle with this big semicircle, this point as point L. And finally, we define the point of tendency of tangent AC with this small circle, this point as point K. Here we can implement the Pythagoras theorem on the big right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC, and therefore the square of the hypotenuse is AC squared. And AC squared must be equal to AB squared plus BC squared. Here by PT is a variation for Pythagoras theorem. Okay, again, according to the Pythagoras theorem, in the right triangle ABC, AC squared equals to AB squared plus BC squared. Okay. AC is the missing side, so we leave it as it is. AC squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BC squared. BC is 8, therefore BC squared is 8 squared, that is 64. So in total, AC squared equals to 36 plus 64, that is 100. So AC squared equals to 100. We take a root out of this equation, and finally we get that the missing hypotenuse AC of the right triangle ABC, it is equals to the square root of 100, that is 10. So AC, the hypotenuse AC equals to 10 units in its length. Write it down. Here we can implement rule 2. If we focus on this common example point A, from this common example point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. So I write it down. According to rule 2, AB equals to AH. What it is given as the question that AB equals to 6 units in its length. So I can write here that AB equals to 6. And from this equation, AB equals 6 equals to AB equals to AH. We derive that AH is also equals to 6 units in its length. This is line segment AH that is equals to 6 units in its length. So I write it down. AH equals to 6 units in its length. What is the length of line segment HC? HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. So I write it down. HC equals to 4 units in its length. In the next step, we will join points. We join points Q and H together by straight line. Point Q is the center of this semicircle. Point H is the point of this big semicircle itself. Therefore, QH is the radius of this big semicircle. We will define the radius of this big semicircle as B. Therefore, QH equals to B. Here we can implement rule 1. Why? Because we have the radius QH is equals to B. The radius QH is drawn to point H, that is the point of tendency or tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can here the right triangle QHC. This is the right triangle QHC. In the right triangle QHC, we have this is angle C. But this angle C is a common angle that also belongs to the big right triangle ABC. So angle C is the common angle that belongs to both triangles, triangle HQC and the big triangle ABC. So we will define the size of this angle C as alpha. And we will focus on this right triangle HQC. In the right triangle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the right big triangle, triangle ABC. In the right big triangle, triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. For the same reason, according to the rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the right big triangle ABC is similar to this right small triangle, triangle HQC. So I'll write it down. We will prove that the right big triangle, triangle ABC is similar to this right small triangle, triangle HQC. So why the right big triangle ABC is similar to this right small triangle HQC? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle ABC, the right big triangle ABC, and it is equal to this angle, that is actually angle QHC, in the right small triangle QHC. So repeating again, actually found out that angle ABC, the right big triangle ABC equals to angle QHC, in the right small triangle HQC, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So you can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to angle alpha as it belongs to the right big triangle ABC, it will be defined as angle ACB, and it equals to itself. If we relate to angle alpha as it belongs to the right small triangle HQC, it will be defined as angle HCQ. Repeat again. This equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle BAC in the right big triangle ABC, and it is equal to this angle, that is actually angle HQC in the right small triangle HCQ. So repeat again. We actually found out that angle BAC in the big right triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the triangles in the right big triangle ABC are correspondingly equal to all the triangles in this right triangle HQC. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. Actually found out that the right big triangle ABC is similar. This is the sign of similar to the right small triangle HCQ according to angle similarity rule. And from the fact that the right big triangle ABC is similar to the right small triangle HQC, we will derive that the following relationship exists between their sides. We will derive that side AB in the right big triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. So I'll repeat again. That side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the small right triangle A equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB is 6 over HQ. HQ is B, it is the radius of the big circle. It is the radius of the big semicircle. So HQ is B, and it is equals to BC. BC is 8 over HC. We already found out that HC equals to 4 units in its length. So in conclusion, we actually found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So we actually found out that 6 over B equals to 2. We multiply this equation by B and finally found out that 6 equals to 2B. Here we will divide this equation by 2 and finally get that B, the radius of the big semicircle B, equals to 6 over 2, that is 3. So we found out that the radius B of this big semicircle equals to 3 units in its length. So, point Q is the center of this big semicircle, point B is the point on the big semicircle itself, therefore QB is the radius of this big semicircle, and the radius of the big semicircle equals to 3. So I write it down, PQ equals to 3 units in its length. In the next step, we join points P and N together by straight line. Point P is the center of this small circle. Point P is the center of this small circle. Point N is the point on the small circle itself. Therefore, Pn is the radius of this small circle. That is the radius that we are looking for in this question. We will define the radius Pn of this small circle as A. So Pn equals to A. It is the radius of the small circle. Again, it is the radius that we are looking for in this question. Here we can implement rule 1 because we have the radius Pn is equals to A. The radius Pn is going to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by straight line. PK is the radius of this small circle, that is equal to A according to our definition. Again, we have the radius PK that is drawn to point K, that is the point of tendency of tangent AC with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, from an external point of a circle, you draw two tangents to that circle. We have here, this is the common external point P. From this common external point P, we will draw two tangents to this circle, tangent PA and tangent PB. By drawing those two tangents, we can get here angle APB. Again, angle APB was created by drawing two tangents, tangent PA and tangent PB from this common external point P. And according to this rule 15, then the angle that will be created between the two tangents, the angle that was created by tangent PA and tangent PB is angle APB. This is angle APB, and according to rule 15, its angle bisector, the angle bisector of this angle APB must pass through point O, that is the center of this circle. Again, whenever you draw two tangents from a common standpoint of a circle towards the circle, you will create angle APB. The angle bisector of this angle APB, that is OP, it must pass through point O, that is the center of this circle. Okay, so we can actually implement rule 15 in our drawing. Why? Because in our drawing, we will focus on this common standpoint, point A. From this common standpoint, point A, we have two tangents to this small circle, tangent AN and tangent AK. So by drawing the two tangents AN and AK from this common standpoint, point A, we created this angle, angle A. Again, angle A was created by drawing tangent AN and tangent AK towards this small circle. According to rule 15, the angle bisector of this angle A must pass through point B, that is this, the center of this small circle. Again, the angle bisector of this angle A must pass through point B, that is the center of this small circle. So we join points B and A together by straight line. So according to rule 15, actually PA is the angle bisector of this angle A. So it is obvious that PA passes for point B, that is the center of this small circle. So in conclusion, we can write down that the angle bisector of angle A, the angle bisector of this angle A passes through point B, that is the center of this small circle. So I write it down. The angle bisector of angle A passes through point P. It is actually the center of this small circle. Okay. Likewise, we continue to focus on this common standpoint, point A. From this common standpoint, point A, we have two tangents towards this big semicircle, tangent AB and tangent AH. And whenever you have two tangents from a common standpoint, point A, you can implement rule 15. According to rule 15, the angle that was created by drawing tangent AB and tangent AH towards this big semicircle is the same angle, angle A. Because the angle was created between tangent AB and tangent AH. So it is the same angle, angle A. According to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. Again, the angle bisector of this angle A must pass through point Q, that is the center of the big semicircle. So it is known, actually found out that the angle bisector of the same angle, angle A, the angle bisector of angle A passes also for point Q, that is the center of the big semicircle. Okay, and again, the angle bisector of the same angle, angle A, passes also for point Q, that is the center of this big semicircle. So I will draw the angle bisector of angle A, that is actually AQ. AQ is the angle bisector of angle A. So we join points A and Q together by a straight line. You can see that the angle bisector of this angle A passes also for point Q. It is obvious that the angle bisector of angle A must pass also for point A. Okay, so I write it down. The angle bisector of the same angle, angle A, passes also for point A. In conclusion, if we found out that the angle bisector of this angle A passes for points A, P, and Q. So I write it down. Actually found out that the angle bisector of angle A passes for points A, P, and Q. Again, the angle bisector of this angle A passes for points A, P, and Q. But the angle bisector of any angle is a straight line, and therefore the angle bisector of angle A is also a straight line. So we can write down that the 3 points A, P, and Q, they all pass for a straight line. The 3 points, they pass for the angle bisector of A. The angle bisector of A is a straight line, therefore all the 3 points, and they are passing for a straight line. The 3 points A, P, and Q, and they are all located on the same straight line. And the straight line is actually the angle bisector of A. Again, the straight line is the angle bisector of A. So the 3 points A, P, and Q, they are located on the same straight line. Again, the straight line is the angle bisector of A. One can say that APQ is one straight line. Again, APQ is one straight line. Line segment APQ is one straight line. And if APQ is one straight line, again, if APQ is one straight line, it means that AQ is also a straight line. So I write it now. AQ is a straight line. AQ is a straight line. And if AQ is a straight line, it means that this shape ABQ is a right angle. Okay, if AQ is a straight line, it means that shape ABQ is a right angle. So I did know, I should have found out that shape ABQ is a right angle. And in the right triangle ABQ, this is the right triangle ABQ, we will define the size of angle A as 2 theta. Again, we will define the size of angle A as 2 theta. And the angle bisector QA bisects angle theta into 2 halves. Each half equals to theta, of course. Likewise, the angle bisector PA of the same angle A bisects angle theta also into 2 halves. Each half equals to theta. So in the right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this missing third angle must be equal to 90 degrees minus theta. Actually, angle theta is a common angle that belongs to both triangles. Angle theta belongs to the small right triangle A and P, and this angle theta also belongs to the big right triangle ABQ. The next step will focus on the small right triangle A and P. The small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus theta. So write it down. In the next step, we will prove that the right big triangle ABQ is similar to this right small triangle A and P. So I write it down. We prove that the right big triangle ABQ is similar to this right small triangle A and P. So why the right triangle A and P is similar to the big right triangle ABQ? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABQ with the right big triangle ABQ. And it is equal to this angle, that is actually angle ANP in the small right triangle APN. And again, I actually found out that angle ABQ equals to angle ANP. Angle ABQ in the right big triangle ABQ equals to angle ANP in the small right triangle APN. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. So we can write now that angle theta equals to itself. It's a common angle that belongs to both triangles. So if we relate to this angle theta, as it belongs to the big right triangle ABQ, it will be defined as angle BAQ. And it equals to itself, so if we relate to angle theta, as it belongs to the small right triangle ANP, it will be defined as angle NAP. So angle theta equals to itself is a common angle that belongs to both triangles. And again, this equation means that angle theta equals to itself. We just called to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is angle AQB in the right big triangle ABQ, and it is equal to this angle, that is actually angle APN in the right small triangle ANP. Repeat again, if we found out that angle AQB in the big right triangle ABQ equals to angle APN in the small right triangle ANP, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So if we proved that all the triangles in the big right triangle ABQ, again, all the triangles in the big right triangle ABQ are correspondingly equal to all the triangles in the right small triangle ANP, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the right big triangle ABQ is similar. This is the sign of similar to the right small triangle ANP according to angle similarity rule. And for the fact that the right triangle ABQ is similar to the right triangle ANP, we derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABQ over side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB is 6 over AN. AN is the missing side, so we we leave it as it is, equals to BQ. BQ is the radius of this big semicircle, that is 3 over NP. NP equals to A. This is the radius that we are looking for in this question. We are looking for the radius of this small circle, that is A. So NP equals to A. So in conclusion, we actually found out that 6 over AN equals to 3 over A. Here we cross multiply this equation and we get that 6A equals to 3 times AN. Here we divide this equation by 3 and finally get that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So we found out that this missing side AN equals to 2A units in itself. So I write it down. AN equals to 2A. AB equals to 6. AN equals to 2. Therefore, the missing 9/7 NB equals to AB, that is 6, minus AN, that is 2A. Total NB equals to 6 minus 2A. Okay, so I write it down. 9/7 NB equals to 6 minus 2A. The next step, from the center of this small circle, that is to say from point P, we will go perpendicular on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we can deduce quadrilateral NPBZ. This is quadrilateral NPBZ. Inside quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBZ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to quadrilateral NPBZ as a rectangle because it has 4 right angles. So I write it down. This is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle NPBZ, side NP must be equal to the opposite side BZ. But NP is A. It is the radius of this small circle, that is A. So BZ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBZ, side NB must be equal to the opposite side PZ, but NB equals to 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. So write it down, PZ equals to 6 minus 2A. What is the length of this 97 ZQ? From the drawing, it is very easy to see that ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. BQ is 3, BZ is 8, so in total ZQ equals to 3 minus 8. So I write it down. ZQ equals to 3.8 units in its length. What is the length of PQ? Actually, we will find out the length of PQ by implementing Rule 10 in our drawing. In our drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at this point L. And whenever you have an external notch between two circles, you can implement Rule 10. So I'll repeat quickly on Rule 10. According to Rule 10, if two circles touch each other externally, then the straight line that connects the centers together must pass for their touching point. In the drawing, we have two circles, and they are touching each other externally in this point P. And according to this rule, Rule 10, the center of this small circle is at point M. The center of this big circle is here at point O. The straight line that connects the centers together is of course the straight line MO. And this straight line MO must pass through point P, that is their touching point. Again, this straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. We can actually implement Rule 10 in our drawing. Why? Because in our drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally in this point N. Therefore, we can implement Rule 10. According to Rule 10, the center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects their centers together is of course the straight line PQ. This straight line PQ must pass through point L, that is their touching point. Again, according to Rule 10, this straight line PQ must pass through point L, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line. If PLQ is one straight line, it means that PQ is also a straight line. Again, PQ is a straight line. And what is the length of the straight line PQ? PQ, because of the fact that PLQ is one straight line, it means that PQ in total will be equal to PL plus LQ. Again, PQ equals to PL plus LQ. So I'll write it down. PQ equals to PL plus LQ. So PQ equals to PL. PL is the radius of this small circle. That is the radius that you're looking for. And it is equals to A according to our definition. LQ is the radius of this big semicircle. That is equals to 3. So in total, PQ equals to PL, that is A, plus LQ, that is 3. So in total, PQ equals to L plus 3. Again, PQ equals to A plus 3. So, in the next step, I'll copy this green right triangle PZQ in the new page, and we will implement the Pythagoras theorem on this right green triangle PZQ. ZQ, side ZQ equals to 3 minus A, PZ equals to 6 minus 2A, and the hypotenuse PQ equals to 3 plus A. Here by PT is a evaluation for Pythagoras theorem. So actually, this is the green right triangle PZQ that are going from the original drawing. In this main right triangle PZQ, according to the Pythagoras theorem, PQ square, that is the square of the hypotenuse, equals to PZ square plus ZQ square. Repeat again, the right triangle PZQ, according to the Pythagoras theorem, PQ square equals to PZ square plus ZQ square. The hypotenuse PQ is 3 plus 8, therefore PQ square is 3 plus A square, and it is equals to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square plus ZQ square. ZQ is 3 minus 8, therefore ZQ square is 3 minus A square. So in conclusion, we found out that according to the Pythagoras theorem, the right triangle PZQ, 3 plus A square equals to 6 minus 2A square plus 3 minus A square. We'll open the brackets on both sides of this equation, and we get that three plus A square equals to 3 squared, that is 9, plus A squared, plus 2 times 3 times A, that is 6A, and it is equals to 6 minus 2A squared. 6 minus 2A squared equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6 is minus 12, and minus 12 times 2A is minus 24A, plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times A, it is minus 6A. So here we have 9 on both sides of the equation, so 9 will get cancelled. And we have also A square on both sides of the equation, so A square also gets cancelled. After we cancel those two expressions, in this side of the equation we are left only with 6A. In the other side of the equation we have here 36 plus 4A squared. We have here minus 24A minus 6A is minus 30A. So in conclusion, we found out that 6A equals to 36 plus 4A squared plus 30A. Here we subtract 6A from this equation, and we get that in this side of the equation, after we subtracted 6A, we left with nothing, that is to say 0. On the other side of the equation, we have 36 plus 4A squared, and minus 30A minus 6A is minus 36A. So in conclusion, we found out that 36 plus 4A squared plus 36A equals to 0. Here we divide this equation by 4, and we get that 4A squared over 4 is A squared, minus 36A over 4 is minus 9A, and 36 over 4 is 9. 0 over 4 is 0. So we should found out that A squared minus 9A plus 9 equals to 0. Actually, this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus C equals to 0. In this general formula for quadratic equation, A, B, and C are the coefficients of this quadratic equation, and X is the variable that we are looking for. And we find out the value of X according to the general formula. X equals to minus B plus minus square root of B squared minus 4 times A times C over 2A. In our specific quadratic equation, that is to say, A squared minus 9A plus 9 equals to 0, the variable that we are looking for is A. Therefore, X equals to A. The coefficient A equals to 1. The coefficient B equals to minus 9, and finally the coefficient C equals to 9. The only thing that is left to do is to put the data of our specific quadratic equation in this general formula for X, and we will find out the value of the values of A, because X equals to A. We will do it now, and we will get that X is A, so A equals to minus B. B is minus 9, therefore minus B is minus 9, that is plus 9, plus minus square root of B squared. B is minus 9, therefore B squared is minus 9 squared, that is 81, minus 4 times A. A is 1, therefore minus 4 times 1 is minus 4, times C. C is 9, and minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 over 2A. A is 1, so 2A is 2 times 1, that is 2. In conclusion, we actually found out that A equals to 9 plus minus square root of 81 minus 36 is 45. So inside the root we have only 45 over 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 9 plus square root of 45 over 2. This expression, 9 plus square root of 45 over 2, is greater than 3. A is the radius of the small circle, that is the radius that we are looking for in this question, and the radius of the small circle is greater than 3 units according to the first solution. But the radius of this small circle A cannot be greater than 3. Why? Because the radius of the big semicircle equals to 3 units. The big semicircle is definitely bigger than the small circle, and therefore the radius of the big semicircle must be greater than the radius of this small circle. That is to say, the radius of this big semicircle, that is 3, must be greater than the radius of this small circle. That is to say, A must be smaller than 3, because the radius of this big semicircle is 3, and A must be smaller than 3. And according to the first solution, A is greater than 3. So this solution is incorrect solution. We cancel the solution, and we're left only with the second solution that is possible for A. According to the second solution for A, the radius of the small circle equals to 9 minus 4 to 45 over 2. So A equals to 9 minus 4 to 45. We'll substitute 45 by 9 times 5 over 2. So according to the second solution for A, the radius of the small circle equals to 9. Here the square root of 9 is 3, so it is minus 3. Inside the root we left only with 5 divided by 2. So according to the second solution for A equals to 9 minus 3 times square root of 5 over 2, or in terms of numbers it is equals to 1.146 units. That is of course smaller than the radius of this big semicircle, that is 3. In conclusion, we found out that the radius A of this small circle equals to either 9 minus 3 times square root of 5 over 2 units. In terms of numbers, the radius A of this small circle equals to 1.146 units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found the radius of this small circle. So in the drawing we have a big triangle ABC. We know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. Inside this big right triangle ABC we have this small circle and we have this big semicircle. The small circle touches the big semicircle at point L. And our mission is to find out the radius of this small circle. So first of all, we implemented the Pythagoras theorem on the big right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. The hypotenuse in this big right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and it must be equal to AB square plus BC square. Repeat again, in the right triangle ABC, according to the Pythagoras theorem, AC square equals to AB square plus BC square. AC is the missing side, so we will leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in conclusion, we found out that AC square equals to 36 plus 64, that is 100. AC square equals to 100. We took out all of this equation and found out that the length of the hypotenuse AC is 10. Okay, AC equals to the square root of 100, that is 10. So the hypotenuse AC of this right triangle ABC equals to 10 units in its length. In the next step, we defined the relevant points to this question with letters. We define the center of this small circle, this point as point P. We define the center of this big semicircle, this point as point Q. We define the point of tendency of tangent AB with this small circle, this point as point N. We define the point of tendency of tangent AC with this small circle, this point as point K. We define the point of tendency of tangent AC with this big semicircle, this point as point P. And finally, we define the touching point between this small circle and this big semicircle, this point as point L. Here we can implement all two. Because if we focus on this common extent point A, from this common extent point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. This is to say AB equals to AH. AB equals to AH. If it again, according to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. You get that AB equals to AH. But AB is 6 according to what is given us the equation. And from this equation 6 equals to AB equals to AH, we will derive that AH equals to 6 units in its length. This is line segment AH and it is equals to 6 units in its length. What is the length of line segment HC? HC equals to AC minus AH. Again, HC equals to AC minus AH. AC is 10, AH is 6, so in total HC equals to 10 minus 6, that is 4. Okay, so in the next step, we join points Q and H together by straight line. Point Q is the center of this big semicircle, point H is a point on the big semicircle itself, therefore QH is the radius of this big semicircle. We define the radius of this big semicircle as B, so QH equals to B. Actually, by doing this construction, we're going to do the right triangle QHC. The right triangle QHC, where this is angle C, but this angle C is a common angle that belongs also to the big right triangle ABC. So we define the common angle C is alpha. In the right triangle QHC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, it is the sum of the angles in any triangle. Likewise, if we focus on the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third angle must be equal to 90 degrees minus alpha according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the right big triangle ABC is similar to this small right triangle HQC. So why triangle ABC is similar to triangle QHC? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can find out that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the angles in the right triangle ABC are correspondingly equal to all the angles in the right triangle HQC, therefore those two right triangles are similar to each other according to angle similarity rule. So I repeat again, the right triangle ABC, the right big triangle ABC is similar, this is the sign of similar, to the right small triangle HCQ according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Repeat again. We will derive the side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB6 and AB6 over HQ. HQ is B, it is the radius of the big semicircle. BC is 8 and HC is 4. So if we found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So 6 over B equals to 2. We multiply this equation by B and finally found out that 6 equals to 2B. We divided this equation by 2 and finally found out that the missing radius B of the big semicircle equals to 6 over 2 is 3. Equals to 3 units in its length. PH is the radius of this big semicircle is equals to B equals to 3. Point Q is the center of this big semicircle. Point B is the point on the big semicircle itself. So therefore, QB is also the radius of this big semicircle is equals to 3. In the next step, we join points P and N together by a straight line. Point P is the center of this small circle. Point N is the point on this small circle itself. Therefore, Pn is the radius of this small circle. That is the radius that we are looking for in this question. We define the radius Pn as A. Therefore, Pn equals to A. And we define the radius of this small circle as A. Therefore, Pn equals to A. Can implement rule 1 because we have the radius Pn that is known to point N, that is the point of tendency of tangent AB with this small circle. Whenever you have a radius that is known to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Okay. In the next step, we also join points P and K together by a straight line. PK is the radius of this small circle, that is equals to A. The radius PK is known to point K, that is the point of tendency of tangent AC with this small circle. Whenever you have a radius that is known to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is actually rule 15. According to rule 15, if from an external point of a circle, you draw two tangents to that circle, then the angle bisector that will be created between the two tangents, its angle bisector must pass through the center of the circle. So, in the drawing, we have, this is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we created here this angle APB. This is the angle APB that was created by the two tangents PA and PB. According to this rule 15, the angle bisector of angle APB must pass through point O, that is the center of this circle. Again, the angle bisector APB that was created by drawing the two tangents PA and PB, the angle bisector must pass through point O, that is the center of this circle. So whenever you draw two tangents from a common external point and from any common external point to a circle, you will create an angle between the two tangents, and the angle bisector of that angle must pass through the center of the circle. So actually, can implement rule 15 in our drawing. Why? Because in our drawing, here the common external point A. From the common external point A, we have two tangents to this small circle, tangent AK and tangent AN. By drawing the two tangents AK and AN, we created there angle A. Again, angle A was created by drawing two tangents to this circle, tangent AK and tangent AN. According to rule 15, the angle bisector of this angle A must pass from point B, that is the center of this small circle. Again, the angle bisector of angle A must pass through point B, that is the center of this small circle. But again, I should found out that according to rule 15, the angle bisector of angle A passes through point B. Likewise, we continue to focus on this common external point A. From this common external point A, we have two tangents to the big semicircle, tangent AB and tangent AH. according to rule 15. So by drawing the two tangents AB and AH, we created the same angle, angle A. Again, angle A was created by drawing tangent AB and tangent AH towards this big semicircle. According to rule 15, the angle bisector of this angle A must pass for point Q, that is the center of this big semicircle. Okay? Again, the angle bisector of this angle A must pass for point Q, that is the center of this big semicircle. Now here, the angle bisector of the same angle, angle A, passes also for point Q. Passes for point Q. It is obvious that the angle bisector of this angle A must pass also for point A itself. Okay? The angle bisector of angle A must pass, of course, for point A itself. So in conclusion, we can write down that the angle bisector of this angle A passes for points A, P, and Q. Again, the angle bisector of this angle A passes for points A, P, and Q. Repeat again, we shall find out that the angle bisector of angle A, the angle bisector of angle A passes for points A, P, and Q. Okay, the angle bisector of angle A passes for points A, P, and Q. But the angle bisector of angle A is, of course, a straight line. And therefore, we can write down that points A, P, and Q passes for the same straight line. What is the straight line? The straight line is the angle bisector of A. Again, then the 3 points A, P, and Q, they are all passing for the angle bisector of angle A, that is a straight line. Therefore, all the 3 points are located on the same straight line. What is the straight line? The straight line is the angle bisector of angle A. Okay, so we can write down that the 3 points A, P, and Q, they are all located on the same straight line. And the straight line is the angle bisector of A, because the angle bisector of A is a straight line. Or in other words, we can also say that line segment APQ is one straight line. Again, line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. Again, AQ must be also a straight line. If AQ is a straight line, it means that shape ABQ is a right triangle. Again, shape ABQ is a right triangle. And here, in the right triangle ABQ, before that, we define the size of angle A as 2 theta. And therefore, the angle bisector QA bisects angle theta into 2 halves. Each half must be also equal, of course, equals to theta. Likewise, the angle bisector PA of the same angle A bisects angle A into 2 halves. Each half equals to theta. So in the right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta. Actually, angle theta is a common angle that belongs to both triangles. Angle theta belongs to the big right triangle ABQ, and angle theta also belongs to the small right triangle ANP. So in the small right triangle ANP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. In the next step, we proved that the right big triangle ABQ is similar to the right small triangle ANP. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both angles, so we can write down that angle theta equals to itself. It's a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we should prove that all the angles of the big right triangle ABQ are correspondingly equal to all the angles of the small right triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, we actually proved that the big right triangle ABQ is similar, this is the side of similar, to the small right triangle A and P according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB6, AN is the missing side, so we leave it as it is. BQ is free, it is the radius of the big semicircle that is free. BQ is free, and NP is A is the radius of the small circle, that is the radius that we are looking for in this question. So in conclusion, we should find out that 6 over AN equals to 3 over A. Here it was multiplied this equation, and finally found out that 6A equals to 3AN. We divided this equation by 3 and finally found out that the missing side AN equals to 6A over 3. 6A over A is opposed to A. So if we found out that this is the missing side AN, this is equal to 2A units in its length. AN equals to 2A, AB equals to 6, and therefore the missing side segment NB must be equal to AB minus AN. AB is 6, AN is 2A, so in total the missing side NB equals to 6 minus 2A. In the next step, from the center of this small circle, that is to say from point P, we draw perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, quadratic quadrilateral NPBZ. In quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in the quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBZ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we will relate to quadrilateral NPBZ as a rectangle because it has 4 right angles. Okay. What is the length of the missing side ZQ? ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. BQ is 3, BZ is 8, BZ is 8, so in total BQ equals to 3 minus 8. What is the length of PQ? In order to find out the length of line segment PQ, we implemented rule 10 in our drawing. In our drawing, we have an external notch between this small circle and this big semicircle. That is to say they are touching each other externally at point L. And whenever you have an external notch between two circles or semicircles, you can implement rule 10. Repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching point. So in the drawing we have two circles. Those two circles are touching each other externally at point P. Therefore they have an external notch between them. The center of this small circle is at point M. The center of this big circle is at point O. And the straight line that connects the centers together is of course the straight line MO. The straight line MO must pass through point P, that is their touching point. I repeat again, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. We can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle. That is to say they are touching each other externally at point L. Therefore, we can implement here rule 10. The center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is the straight line PQ. The straight line PQ must pass through point L, that is their touching point. Again, the straight line PQ must pass through point L, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line. If PQ is one straight line, it means that PQ is also a straight line. And the length of PQ will be equal to PL plus LQ. Again, PQ equals to PL plus LQ because PLQ is one straight line. Again, PQ equals to PL plus LQ. PL is the radius A of the small circle. This is the radius that we are looking for in this question. Plus LQ. LQ equals to 3. It is the radius of the big semicircle. That is 3. So in total, PQ equals to A plus 3. The next step, I copied the right triangle PZQ in a new, the right crane triangle PZQ in a new page, and we implemented the Pythagoras theorem in the right crane triangle PZQ. This is the right crane triangle PZQ that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Repeat again. According to the Pythagoras theorem, in the right triangle PZQ, PQ square equals to PZ square plus ZQ square. PQ is 3 plus A, therefore PQ square is 3 plus A square, and it is equals to PZ. PZ is 6 minus 2A, 6 minus 2A, therefore PZ square is 6 minus 2A square, plus ZQ square. ZQ is 3 minus A, therefore ZQ is 3 minus A square. So in conclusion, according to the Pythagoras theorem, I shall find out that 3 plus A square equals to 6 minus 2A square plus 3 minus A square. We open the brackets on both sides of the equation, and we actually found out that 3 plus A square equals to 3 squared, that is 9, plus A square, plus 2 times 3 times 8, that is 6A, and it is equal, the other side of the equation, we have 6 minus 2A square. 6 minus 2A square equals to 6 squared, that is 36, plus 2A squared. 2A squared is 4A squared, plus 2 times 16, that is minus 12. Minus 12 times 2A is minus 24A. And we have here 3 minus A squared is 3 squared, that is 9. Plus A squared, minus 2 times 3 times A, that is minus 6A. So here we have 9 on both sides of the equation. So 9 will get cancelled, and we have also A squared on both sides of the equation, so A squared also will get cancelled. After we cancel those two expressions, we left in this side of the equation only with 6A. On the other side of the equation, we have 36 plus 4A squared, and here we have minus 24, minus 24A minus 6A is minus 38. So in conclusion, we found out that 6A equals to 36 plus 4A squared minus 38. Here we subtracted 6A for this equation, and finally found out after we subtracted 6A, in this side of the equation we have nothing, that is to say 0. On the other side of the equation we have 36 plus 4A squared, and minus 38 minus 6A is minus 36A. So in conclusion, we found out that 36 plus 4A squared minus 36A equals to 0. Here we divided this equation by 4, and finally found out that 4A squared over 4 is A squared. Minus 36A over 4 is minus 9A, and 36 over 4 is 9. So in conclusion, we found out that A squared minus 9A plus 9 equals to 0. This is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. This general formula for quadratic equation, A, B, and C are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, general formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a, therefore x equals to a, the coefficient a equals to 1. The coefficient b equals to minus 9, and the coefficient c equals to 9. So the only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x, and we find out the value of the values of a, because x equals to a. We did it and found out the thing, again x equals to a, so a equals to minus b. b is minus 9, therefore minus b is minus 9, that is plus 9. Plus minus square root of b squared. b is minus 9, therefore b squared is minus 9 squared, that is 81. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c, that is 9. Minus 4 times 9 is minus 36. So in total, inside the root, we have 81 minus 36 over 2a. a is 1, so 2a is 2 times 1, that is 2. So here actually found out that a equals to 9 plus minus square root of 81 minus 36 over 2. 81 minus 36 is 45, so inside the root we have to only be 45. We actually found out that a equals to 9 minus square root of 45 over 2. A equals to 9 plus minus square root of 45 over 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 9 plus square root of 45 over 2. This expression is greater than 3. That is to say, according to the first solution for A is the radius of this small circle. According to the first solution, the radius A of this small circle is greater than 3 units. But it is impossible that the radius of this small circle is greater than 3, why? Because of the fact that the radius of this big semicircle equals to 3 units, and the big semicircle is definitely bigger than the small circle. Therefore, the radius of the big semicircle must be greater than the radius of the small circle, or the radius of the small circle must be smaller than the radius of the big semicircle. Therefore, the radius of the small circle A must be smaller than 3. Therefore, this solution for A that is greater than 3 is the correct solution. We can set the solution, and we'll have to live with the second solution that is possible for A. The second solution for A is that A equals to 9 minus square root of 45 over 2. We started 45 by 9 times 5 and found out that A equals to 9 minus square root of 9 times 5 over 2. The square root of 9 is 3, so in total inside the root we have only 5. In conclusion, I actually found out that the radius A of the small semicircle equals to either 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, the radius A equals to 1.146 units. Okay, again, we actually found out that the radius A of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, so in terms of numbers, the radius A of this small circle equals to 1.146 units. That is definitely less than 3, that is the radius of this big semicircle. Okay, thank you very much.